It is clear to see that designing against the possibility of soil liquefaction is a big issue for places that experience earthquakes. Iwasaki developed a simplified method to analyze soil's potential for liquefaction. This method is based on a liquefaction resistance factor, which indicates the liquefaction potential at a certain depth, and a liquefaction potential factor, which indicates the potential liquefaction on site. The resistance factor can be expressed as R divided by L, where R is the undrained cyclic strength and can be calculated using equations 1 and 2, depending on the average size of the soil diameters. L can be calculated using equation 3, where tau is the max shear stress, g is the acceleration of gravity, alpha s is the acceleration at ground surface, and z is depth of soil. The potential factor is calculated using equation 4, where F is 1 minus the resistance factor if the resistance factor is less than 1, and F equals 0 if resistance factor is greater than 1. Therefore, if there is a large resistance to liquefaction, the potential for liquefaction is 0. In words, the lower the resistance factor, the greater the severity of liquefaction. The greater the potential factor, the greater chances of liquefaction to occur. In 1964, liquefaction was observed after the Nagata earthquake in Japan, and both resistance factors and potential factors were calculated for both liquefied and non-liquefied sites. It was proven that generally resistance factor is less than 1 for liquefied sites and greater than 1 for non-liquefied sites. Using these values of resistance factor, potential factor was then calculated on different depths, and the results are as followed. When potential factor is 0, potential liquefaction is very low. If the potential factor is between 0 and 5, potential liquefaction is low. However, for certain types of buildings that have high risk, further investigation may be needed. If the potential factor is between 5 and 15, liquefaction potential is high and further investigation should be done. If the potential factor is greater than 15, liquefaction potential is very high and further investigation will be needed, along with foundation design that will mitigate liquefaction damage. As shown in the introduction, the most used deep foundation design for mitigation of liquefaction-induced damage is end-bearing piles. End-bearing piles are used to transfer the load from the superstructure down to a layer of soil that is strong enough to hold the required load from the superstructure. The seismic response of pile foundations during an earthquake is very complex. It is controlled by inertial interactions between superstructure and pile foundation, kinematic interaction between foundation, soils, and piles, and the stress-strain behavior of the foundation soil. All these interactions occur simultaneously with ever-changing soil properties as liquefaction occurs. Because of the complexity, many physical and numerical models have been developed in order to fully understand the interaction during liquefaction of soil on a pile. Physical modeling has been developed into the main tool used to study lateral spreading. However, they are not time efficient nor always necessary. Physical models include shake table tests, centrifuge tests, and full-scale field tests. Numerical methods have been developed to analyze pile response to liquefaction. However, most are very sophisticated and require knowledge and understanding of very specific data inputs. Because of the complexity, certain codes have been developed to bypass the analysis aspect in order to design piles. The Japanese Highway Code established the JRA distribution code, which is shown in the figure. The code states that the pile must be designed in order to withstand 30% of the overburden pressure within a liquefied soil layer. This code has been proven to work. However, in certain cases, like the Shawa Bridge, it was proven that the piles were designed to satisfy this code, yet it failed. The problem with the code is that it only takes into consideration the flexure of the pile that causes bending failure. Bhattacharya developed another theory based on buckling. He claims that the pile should be treated as a column that is taking on a massive amount of axial loads from the structure. Now the pile can act as a continuously supported column since it is surrounded by soil that continuously puts pressure on the sides of the columns. However, when the soil liquefies, the pressure from the soil is no longer present. Therefore, the pile becomes unsupported and begins to buckle as shown in the figure on the left. Depending on the thickness of the soil layer that liquefies, the pile could become an unsupported, long, slender column, which is prone to buckling. Bhattacharya claimed that if the Shawa Bridge piles that were shown in the introduction were designed to withstand buckling as well as bending, the bridge would not have failed. He proved this to be true. The steps to calculate the critical load, which is the maximum load the pile could carry due to buckling, can be found in my paper. However, the critical load and the actual load for piles in past earthquakes that were deemed long, slender columns were analyzed and compared. If you look at the graph, poor performance occurred when the ratio of actual load to critical load were less than 1, which means that the critical load for buckling was less than the actual load that occurred. This proves that buckling needs to be accounted for when designing piles for liquefaction. As stated in my introduction, soil improvement techniques are also used to mitigate liquefaction-induced damage. Typically, soil improvement techniques are used at sites that have already endured soil liquefaction or under construction with shallow foundations. Therefore, soil improvement techniques that create low vibration are most used. Grouting techniques such as compaction grouting, permeation grouting, and jet grouting are known to have low-level vibration. Once again, grouting is the injection of materials by pumping into the soil or rock formation to change the physical characteristic of the formation. Compaction grouting is the injection of thick grout, typically a soil cement water mixture that has very low mobility. The grout remains a homogeneous mass and does not enter the soil pores. Therefore, it just replaces the surrounding soil with a substance of increased density. The picture shows different applications for compaction grouting, and as you can see in the top right, it is often used to strengthen the soil around a damaged pile. One drawback of compaction grouting is that since it does not enter the pore spaces of the soil, it pushes soil out of the way, therefore disturbing the surrounding area. Permeation grouting, however, is more of a fluid that fills the soil pores spaces, which increases the density of the soil. Permeation not only strengthens the soil by cementation, but it also reduces the amount of water that can flow through the soil, which decreases the possibility of liquefaction. Jet grouting is an erosion-based system that relies on kinetic energy of high velocity jetted to break down the soil structure and remove a portion of it while mixing it with cementation grout. The main use of jet grouting is to create a soil cement column that acts as a wall of an excavation. However, if used properly, jet grouting can contain soil, whereas if liquefaction were to occur, lateral displacement would be minimal, which would minimize the amount of force on a pile. In conclusion, mitigation of liquefaction-induced damage is extremely important. The simplified method for potential liquefaction is a great technique to use in order to quickly know whether liquefaction is even possible. Once liquefaction potential is established, deep foundation design is the best technique to prevent damage to structures. However, it is proven that piles need to be designed against buckling just as much as bending. If a site has already endured liquefaction, soil improvement techniques like compaction grouting or permeation grouting can be very useful in increasing the strength of the soil. Thank you for watching.